Well, welcome to day 3 of this 10-day conference. It feels like it, doesn't it? Simon hasn't. You've only just arrived.
I have, yes.
Yeah, okay.
Yes, because I was at Jay on the beach.
Yeah, you're lucky.
In Malaga.
Yeah. So we're going to take you through, well, you can read the words. So let's get started. My name is Steve Poole. I am the Director of Developer Advocacy at Cernotype. But that's not super important, other than I want to talk about security to you guys. The main reason is that I spent most of my technical career doing JVMs of all sorts of shapes and all sorts of different ways. And so what I want to communicate is a lot about security from a JVM point of view. Just give you some ideas of what's there and what's not. So I work for this company, and most people go, Cernicube? And it's like, no, we're the guys that do this, Maven Central, and we also do a bunch of stuff, one of which is Nexus. So you've probably heard us and probably used the stuff that my company produces. You just hadn't associated the name. Anyway, so that's me.
That's me. If I can hear my... Thank you. Yeah, so that's me. I'm Simon Ritter. I'm the deputy CTO, as I like to say, the understudy to the real CTO at Azul. So quick show of hands. So who here has heard of Azul? Okay, most people. That's good. Good. Okay, so I'm like Steve. I'm old, and I've done Java.
Thank you.
Well, it's true, isn't it? I mean,
It's maybe true. We have to point
because I joined Sun Microsystems in 1996. And a lot of people I talk to now is like, oh yeah, I was at like junior school in 1996, and that wasn't even my first job. Of course, it wasn't even my second job. So I do feel old when I say that. And yeah, I like Steve. I've been doing Java right from the very beginning, and I worked for Sun for 14 years. I worked for Oracle for 5 years, and I've been at this company called Azul for the last nearly 8 years, actually, which is quite incredible. And what we do, if you haven't heard about us, is I make Java better. That's really what we're trying to do, is make Java better for people, and that takes many different forms. One, we do an alternative build of OpenJDK, so it's just a build which we support, same kind of idea as Red Hat supporting Linux. We then have our idea of Platform Prime, which is about high-performance JVM, lower latency, higher throughput. More recently, we've switched to looking at how we can improve things in the cloud. So we have a cloud-native compiler, which is all about reducing cloud costs. And the thing specifically that why I'm here today, when we're talking about security, is this thing that we do, which is Azul Vulnerability Detection. And I'll talk a little bit more about that later on. Okay, so what is this talk not about? That's a very important thing as well. So the first thing that we need to know is we're not talking about some of the things like the security manager. And a lot of people, when they saw this, they said, oh, deprecate the security manager for removal. You're removing security from Java. That's really bad. Except, well, no, it's not, because anybody here used the security manager? No. No? Okay, nobody. Good. See, that's the thing. It's actually more to do with things like applets and Java Web Start and things like that. So nobody really cares about the security manager anymore, so we're going to remove it, which is great. So we won't talk about that. It's also not about some of the replacements that we're seeing in terms of things happening around the JDK. One of those things was strong encapsulation of the JDK internals. This big thing that changed between JDK 8 and JDK 9 that made a lot of developers' lives a bit of a nightmare because suddenly they couldn't access, well, they weren't ever supposed to access things like sunmisc unsafe, and the idea was to turn off access to those. I really like sunmisc unsafe because the clue is in the name. Unsafe. Don't use it. But lots of people obviously did because it gave you better performance. So we're not going to be talking about those things either. So it's more about how does security work in terms of Java, and how does security work in terms of the JVM? Now, because Steve and I have been around for a long time and we've come through all of the history of Java, we can remember back to the very early days of Java. And when Java was created, one of the kind of key goals was to have the ability to move code around the network. And if you want to do that, you need to be able to do it securely, you need to be able to do it safely, because obviously if you're moving code around the network, executing it remotely, that would be a wonderful way to provide viruses. So we don't want that to happen. And right from the very beginning, Java was developed with the idea of security in mind, working in a networked environment, moving code around, executing remote code, all of those sorts of ideas. And a lot of the basics, and Steve's going to kind of dig into this more detail, a lot of the basics is where we come from in terms of that. So simply the idea of when you load a class file, it goes through a 4-step verification to make sure that you can't do something malicious with that code by fiddling with the bytecodes and doing things like that. But Steve's going to talk more about that. But also, including all of the techniques and the facilities that you need to move things around securely, and all of the encryption, all of the TLS type things, all of those sorts of things. So it's much more about looking at how the JVM deals with that. So the other thing that I want to talk about first before Steve gets into his stuff is how do we actually keep the Java platform secure? And again, Java's been around for 28 years. Sometimes people sort of think to themselves, whoa, Java's 28 years old. Surely by now you have eliminated all the security flaws from Java. No, because Java, if you look at it, is around about 7.5 million lines of code. So the idea that you could eliminate all the security vulnerabilities from that is pretty much impossible. We have OpenJDK. It is open source. So how do we keep the Java platform itself secure? Well, we do that in a number of different ways. The first is that there are updates on a regular basis. And when Oracle took over from Sun in terms of really kind of running OpenJDK, they switched to this idea of having quarterly updates which aligned with the way that they update all of the software at Oracle. So it's a very sensible thing to do. And what we do is we see that in January, April, July, and October, there is an update to the JDK. That includes a number of things. It includes a set of security patches that address vulnerabilities that have been reported against Java and which have been resolved, obviously. It also includes bug fixes, some minor enhancements, all of those kind of changes that you might get there. Now, the way that works is that the development of those changes is only done in the current version of Java. So right now that's JDK 20. But obviously, lots of people are still using older versions of Java. And we have these long-term support versions that we know about. So there's JDK 17, JDK 11, even JDK 8. And in the case of Azure, we also support JDK 7 and JDK 6. So those need to be backported to the current, or to the older versions. So what we do is we take those changes and we make sure that all those changes, where applicable, are backported to those older versions. Because clearly if there's something in JDK 17 that doesn't exist in JDK 7 or 8, then there's nothing to backport. Now the way that this works is that there is a special group within OpenJDK called the OpenJDK Vulnerability Group. And the Vulnerability Group was formed a few years ago, really when Oracle made the switch in terms of the speed at which Java would be developed to a 6-month release cadence, and also the fact that they changed some of their licensing terms, which led to a proliferation of OpenJDK distributions. Because of that, Oracle very logically wanted to make sure that those Java distributions could be as secure as possible. To do that, they formed this group within OpenJDK, which consisted of all the sort of usual suspects, if you like, of people who are creating JDK distributions. So IBM is there, Red Hat is there, SAP is there, even Microsoft are there. I find that, as an old-time Java person, seeing Microsoft represented in terms of OpenJDK and so heavily involved in that is quite a bit of a surprise. But the idea behind the JDK Vulnerability Group, as it says here, is a secure private forum in which trusted members of the OpenJDK community receive reports of vulnerabilities in OpenJDK codebases, review them, collaborate on fixing them, and coordinate the release of such fixes. So the important thing here is that this is a private group. Now, I'm actually on the JDK Vulnerability Group, and I see all of the emails that get passed back and forth amongst those people in there. And what we do is we work collaboratively together. So there's all of the engineers from the different companies work on fixing these vulnerabilities as they're reported. And then when we create fixes for them, we put them into the OpenJDK, And when the update comes out, we release those fixes into the source code as well. So it's done in a very sort of sensible way, because what we don't want is to publish any of that information. All of the email we pass back and forth is encrypted. We don't publish any of the emails that are exchanged even after an update is released. We keep everything very secret, because the whole point about security is, making sure that people who try to exploit these things can't understand what's actually going on. So as I said, there's this idea of long-term support, and so we use OpenJDK. We have binary distributions. If you want to use OpenJDK, you have to find a binary distribution, whether it's Oracle, whether it's Azure, whether it's Amazon, Corretto, Temurin, or whoever. And one of the important things about that is that these updates come out on a regular basis. But how quickly do you get access to those updates once the update is released? Because Oracle come out with theirs, and then everybody else follows after them. If you have to wait days or even weeks for an update to be released, that is a time when the fact that the vulnerabilities have been exposed through the CVEs that are reported against that update, there could be time when you actually could be exposed to those vulnerabilities. So that's something to consider. There's also two different forms of each update, and that's another important consideration. The first of those is what we call the critical patch update, or CPU, and that's only the security changes for that particular update. And that's typically less than 15 in size, less than 15 updates. The other form of the update is the patch set update. This is Oracle terminology, or the PSU, and that's the full update. So it's all those security patches plus bug fixes plus enhancements, and that can run to 3, 4, even 500 changes. So having two different versions is quite important, because if you've got a critical vulnerability that needs to be addressed quickly, rolling out the CPU is a much better way of doing it, because there's much less chance of affecting the stability of your applications by changes that are made in terms of other parts of the update. So with that, over to you, Steve.
Thank you. Right.
Hope I haven't taken too much time.
So you heard about the process, the people, the thinking, and that there's these a lot of protections have been thought about right from the beginning. So I'm going to go through those, but you can see what we're going to talk about. I'm going to talk about some of the reasons why this is really, really important, and then go through with the internals. And then there's a couple of secret weapons at the end. If we have time, I'll get to those, and you'll be amazed by those as well. Right. So the most important thing to understand is why this is important. And you have to understand what's happening in the world of cyber attacks. So when I first started talking about security, which is about 2014, 2015, we could equate the value to the bad guys of cyber attacks to about the same as the drug trade. And that was about $450 billion a year. So $450 billion a year is coming out of the economy and going to the bad guys. And 2016, cybercrime just edged over the top of that. And you can see, right, $450 billion gets you 50 US Nimitz carriers, which is a pretty large number. Not quite sure what you do with 50 of them, but there you go, okay? So that's scary enough. Let's roll forward to today-ish. We're now looking at 450 billion? No, we're looking at 6 trillion. 6, lots of zeros. Not 50 carriers, 620. So you can see it's gone up. And the drug trade numbers is about the same. Because drug trade is physical, it's actually manageable. They can, you can't move 100 million times more drugs without being spotted, but you can do a lot more cyber attacks, and because it's easy. And to put this in context once more, because you just have to internalize this. Right? This is how much money is coming out of the global economy. If you said, let's take 6 trillion as a GDP number, where would we fit in the ranking? Well, it turns out that if cybercrime was a country, it would be the 3rd largest. That's how much money is being taken out. And therefore you can see just how important this is, and just how it is becoming, oh, well, what would you call it? Just beyond belief. It is a existential threat for everybody. Right? And this number is just going up. There's the red line is the drug trade. You can see what I said. It's just basically stable. 56% per year. I'd like to make money like that. And the thing is, there's no sign of this stopping. Currently, by the end of middle of 2024, if you do the numbers, it'll be number one because it'll outstrip the US. That's how much money is coming out of the system, right? And so, jokingly, we say that Pablo Escobar was starting again. He'd use a laptop because you can make a lot more money. But joking aside, you can see how bad this is, right? Now, you might go, well, what's that do? What's got to do with me? Well, you've got to understand that the way that these bad guys are getting in is through you, because you choose open source, right? 90% of an application, modern application today, is made up of open source. It's dependencies that you download, and those are being targeted. Right. So now we have very incented people targeting open source projects, trying to compromise them, find existing vulnerabilities, create new ones, take over projects, you name it. All these activities are coming through. And because this stuff is so valuable, where we used to expect to see vulnerabilities being reported and then you fixing it, that's not what's happening. What we're seeing now is by the time any serious vulnerability is reported, it is already being exploited. Log4Shell was the big one, right? So we're in this world. Exploit first. It's about you don't have time to fix, so you have to, patch instantly. So the question is, what else? How do they get in apart from open source? We're talking, this is a JVM talk. So how do they get in? What's the JVM attack vector for these guys? So I've drawn a picture of a JVM, which took me back, sitting there going, oh yeah, I remember you right. So, okay. So what's in a JVM? A bunch of stuff, right? Your dependencies, 90% of your application. Your application sits on stuff, and at the bottom is the operating system. And then in there's the JVM, and there's some JNI, there's some class loaders, there's a JIT, there's stuff, right? And the chances are you probably haven't really thought about it, but these are all the components that you rely on. So what's the first attack vector you can think of? Well, the one that most people will go over like, well, networking, get in through the compromised communications. Well, actually, from a JVM point of view, the protocols that we support, there is a plethora. So actually, trying to compromise the security protocols from a Java point of view is not going to happen, right? Because there occasionally you will get protocol problems, and you will have heard about them. When you get a protocol problem, that's usually a design issue, less likely an embodiment, but it's rare. So we can be happy with that one. That's one way. Another more common way is to get to the bit round your JVM, to get to your config files. Because if I can get into your Docker container, or I can get onto your system, maybe I can change the config files. Can I deal with fiddling around with the execution environments? So that's wonderful way to get in. So does the JVM have any defenses against that? Right? Well, no. And you need to understand, because lots of people go, well, it doesn't matter, because by the time the bad guys got onto my system, they can do whatever they want. And the answer is that's not true either, because there are many vulnerabilities out there, obviously not Java ones, like OS ones, that can sometimes just let them get access to a file, to a directory. So it's quite possible for them to get at a particular file in your system through some other vulnerability and then change things. All sorts of nice stuff they could change. They could add things to your class path. They can fiddle with your parameters. And the simple answer is, that's your problem. JVMs have to assume that their external environment is in safe hands. Right, okay, so what about inside the JVM? Some things you might think about. So can they change the bytecode? Because that would be cool, you know. Can they get in and access memory and change things? That's another, common attack vector. And then loaded code. Can I get loaded? Can I corrupt code? Can I make you load remote code that's bad? Hey, Log4Shell let you do that. Well, you need to look at what actually a JVM is to better answer these questions. Because at one level you might go, well, yeah, you can get into memory, or of course you can change the bytecode, or yes, of course you can get bad code loaded remotely. But the question is that really true? So we have to talk about what a JVM is. And in the interest of time, I'll let you photograph it, but we'll move on. But Simon sort of laid it out, right? The JVM is a virtual machine with a bunch of design principles. So let me give you a better picture. So a JVM is this thing that abstracts real life, hardware, networking, file systems, UI, you name it. Its job is to abstract that into a common identity, a common theory that you can apply, the JVM, right? So you can think of the JVM as this structured abstraction. So there are bits, right? There's an architecture layer, there's separation, there's a compiler, okay? So there's really bits, and their job is to take the outside world and present it to you as in a common way. But actually, it's not even that complicated, because actually, if you look at what a JVM is, it's even simpler. There's a JVM memory model. There's a threading model. There's a model of a CPU. And all these are the things that we abstract. And then basically some code that translates the idea of your application into reality. Because obviously at some point machine code has to be generated, right? And even that is too complicated, because it's actually more like this. The JVM is a very, very, very simple idea of a computer. And it has a very, very simple idea about threading, in that it knows about locks, doesn't understand about threading at all, and has no understanding of memory. It just has object references. That's all it cares about. There is no concept in the core JVM about garbage collection or threading, right? I mean, bits, but basically that's it. So this is the first defense, is that the machine that actually runs is really, really simple. And because it's a virtual machine and it's not real, it's just a spec, it's very hard to use this model against itself to break into things. So we're really lucky to have that model. Okay, right. So let's move on. JVM. Okay. So as I said, it's a stack-based CPU. It's got one register, which is called the program counter, because you need to know where in the stack to run. It's stack-based, which again is different from most other computers. There's no pointers. You cannot create pointers. Pointers are implicit. They have objects and there is a reference, but you can't forge them, because that's not possible. Right? There's no threading. There's no access to the CPU. You cannot break out from this specification into the real world. Right? And that is a massive defense. There's nothing designed, nothing specified for you to do that. So, good place to start. Right. Now, there are, as it says, these unspecified features. If you look at the way that the JVM specs are put together, you've got the JVM, you've got class spec, you've got Java doc, you've got the language, you've got a whole bunch of doc, and they sort of all work together. But the bottom case, the JVM says, I know nothing about memory, I know nothing about threading. So it's applied on top, right? So these unspecified features. So memory management, we have garbage collection, which when we first started doing garbage collection, people went, no, it's been proven never to be any good. right? And here we are, everybody uses garbage collection. So, great. So you can't actually forge an access to an object, and the location of any particular object is not fixed because objects move around. That is a significant defense, because another attack vector is to find out which object, a location in your memory for where your passwords are stored. But they can't, there's no way of doing that. They just move around all the time. Okay, it's really hard. It's hard to get in there and then to find a particular object by coming out from the outside and peering into the heap. It's, you know, it's not impossible, but it's really hard. So that's cool. And then you have the threading, right? It says has an intentionally leaky abstraction, because in the early days, it turned out that if threads are completely oblivious to real life, you can't do some things in terms of like releasing resources, local resources, and things that are thread specific. So there's some of that. So there was a hole, but virtual threads is about to close that. So with virtual threads, they don't even exist either. So breaking out of a virtual thread into real threads is impossible too. So just another way that the JVM design keeps you safe that you hadn't really thought about. Okay. Yeah, second line defenses. The JIT. So how does your code get executed? You've got to remember that your Java code that you create, that lovely bytecode, which you may or may not have looked at, is really just a model of your application. Something has to turn your model into reality, and that's usually the JIT, right? And the JIT understands about the fact that if it was to create, say, do the same memory allocation in the same place, that could be a weakness. So it doesn't. It participates in this idea of allocating objects in different places to keep things moving around. And because we're taking bytecode and turning it to machine code, that process is never ever the same, right? The machine code that you get this instance versus the machine code you get this instance for exactly the same bytecode will change. So again, it's a sort of natural defense that the JIT is generating based on performance profiles, the code that that's going to execute, and it will change. Because it doesn't sit still. It's not done for once, not generated for once. It gets regenerated. So that's really good benefit too. And the JITs, some JITs understand about different types of memory access, and if they can make use of that, they'll do so. So you get all this protection for free. Just-in-time compiler for the win. Yes? Now, the just-in-time compiler is taking all this bytecode, and as I said, this bytecode is just designed for a very simple computer that you can't break out of, right? But it still has some vulnerabilities, and that vulnerability needs to be checked. So one of the obvious things is it is in theory possible to create bytecode that could crash a JVM, and you know there are always some gray areas, and so what we do is we're super wary, and that when we load classes. And we look at the bytecode, a whole bunch of verification takes place. We are looking at will this code execute? What, you know, will it break out? What bad things? Whole list of stuff, right? And it will do that. And we'll do that at load time. And the JIT sort of has to do it as well. Okay, so there's multiple levels of verification going, is this code valid? Is it going to execute properly? Right? And those defenses are just built in. So it is really hard to generate bad bytecode. It's not impossible, but it is pretty hard, and it's really hard to get it to run. Which I think I've just said this. Yeah, branches, it was always looking, you get the idea. Let's move on. Right. What's the next line of defense? Hey, class loaders. Who's heard of class loaders? I think all Java developers should go, yes. Okay, so class loaders, it's a way of keeping code separate. You want to be able to manage where code comes from because you have different ideas of trust. If you load the class path, you load it remotely, right? And some systems, they're out there, that generate loads and loads of class loaders and have really complicated things. Mostly, though, you end up with what you expect, a small number. And the vector that the bad guys will want to do is to get into those values. Can I add classes into? Can I add jars into your extensions class path? Can I add things onto the boot class path? You know, so that they'll try and get into those spaces. Okay, most of the time, that's the major vulnerability. There is some defense in class loading, because in theory, class loaders could apply extra checks based on where they load things. Okay, so it's there because we do make those rules. It's not particularly great, but actually it doesn't really need to have to be. So most of the time, we can say, oh, you loaded that locally, I trust you, or hey, I loaded it remotely. Well, remote code loading. Does anybody remember this? Yeah. Log for shell, right? So log for shell made use of a really nice feature that somebody added into log4j that essentially said, I can specify to a JVM not only that I want to load classes, but also say that if I reference a class that isn't on your class path, you can load it from this remote URL. So this process, which of course was added way afterwards into JVM, because it comes from we added some J and DI, not even when we added J and DI some time ago, but we added J and DI into the system as into the class libraries. It's not a JVM class library problem. And so then we end up in this situation where it is possible for you to load a class that this is of this reference type, and that reference type says to the JVM, any other classes that I reference, if you haven't got them, load them from here. And they can be completely arbitrary, which is why you can imagine log4shell was so bad, because in the absolutely right circumstances, this could happen. Now, there is a defense for this, but it's not a JVM defense. It's a JNDI loader defense. So this is now disabled by default, but it could be re-enabled, right? So the reason this is bad is not just that you can load arbitrary code, given what I said to you about, it's quite hard to break out of this. No, it's what people do with that stuff, which is why I want to segue into this thing, into serialization. The shoot yourself in the foot with both barrels multiple times. And I unfortunately have to confess that I was actually contributed some of the code to adding serialization years ago. But
I was going to say, I think it's one of those features that most people would have said, let's leave it out of Java from the beginning.
Now, but not back then. Back then, we had no way of getting data out of VM into real world. And it was like we have a graph of objects. And so they went, serialization. I mean, it was done in weeks. There was no thought. Yeah. I was a junior programmer. Right. Okay, so segue. So serialization is used everywhere. Sorry?
Leave it to the intern.
Yeah, leave it to the intern. Yeah. It's used everywhere. People go, I don't use serialization anymore. And yes, you do, because everything gets used. There was a recent vulnerability that was based on some well-known piece of application using serialization to do deep copies of things, because you can serialize and deserialize and you get a new set of objects. And you can see it is everywhere. It's not going away, right? Because if you go to GitHub and do object input stream, search for it, this is what you get. Object input stream is the vector in, okay? So the reason it's bad, and I'm going to have to do this quickly to show, but this is what's in the serialization form. Well, this is a table of it, right? The bit I want to point out is the bit at the bottom. Serialization is what's called self-defining. So at the bottom here, let's go down here. Yeah, at the bottom there, you can see it says UTF-8 field name, hello, and class name, Java lang string. That class name isn't the type of the field name. It's the type of the data that's at the bottom. And that's defined by this field type L. So what serialization does is it says, I read all this stuff and I get to this and it says, you're going to load an object of type string. enter this field called hello. It's got nothing to do with what the field type is in the class. It's self-defining, right? So that means, let's carry on. Well, see, I've done all this already. So that means that I can have a string. I could have field name hello. I could put an array in, or I could force it into an integer, right?
So this would actually be really good for JavaScript.
For JavaScript, yeah. So the serialization process will instantiate whatever this is and then trying to put it in the slot. So you will often see this error. Well, hopefully you won't see it often. Cannot assign instance of something to a field. And that's all the bad guys need, because they've made your machine instantiate an object under their control. They forced you to do that. And it doesn't matter that it fails, and sometimes it doesn't fail, but because it fails, you've started code, right, on their behalf. And what I've said about it coming with remote execution, better say I can load any code. I can force your JVM to do whatever I want, right? And as I said, hey, it's a great gift, and it has been, and continues to be, right? And serialization is more prevalent than you realize. If you go implement serializable, which is the interface that you have to start this process, there I went to Google, to GitHub, 15 million, right? That's bad, right? And if you go, well, so what? Well, there are these wonderful things called gadget chains, which exploit this idea of being able to force code of different types to be loaded. And this is a real one, and this goes from object input stream read object, which is where you start the process, all the way down to runtime.exec. Somebody figured out what path of forcing objects to be instantiated in different ways to allow them to call some code that can access your, command line, right? And honestly, there are so many tools out there that will help you do this. This is one. YoSerial is designed to help you do this. Okay. So the question is, what are we doing about it? Well, remote loading has been defaulted off, but it can be turned back on. Remember that people can come and get at your command lines, so they could, in theory, re-enable it. We have some built-in things, serialization filters, where you can put some rules in to say what class patterns you want. It's pretty clunky. 17, we got slightly better ones. The problem is that you've got to specify what you want, so you've got to keep that up. And and it's clunky, but it's there. It is a defense, right? It doesn't defend against some other subtle types of attack, but that's for another day, right? So other things you could do to prevent this is use modularity, because if they're not remote coded loaded, they're remoting code remotely, they're accessing the code on your class path. And if you don't use modules, all code on your class path is available to them. If you use modules, then you can't access the code from a different module. Well, they can't access code from a different module. Okay. Anybody here use modules? Yeah, it's a problem there, isn't there? Okay.
Yeah. 0.
Yeah. Now you can go one step further, and you can do linking. And you can take those modules and the JDK modules and create your own custom runtime if you use modules, right? You have to rebuild it when you need to, but it's much safer because you've chucked away all the code that might be attack vectors, right? Okay, if you don't use modules, you can do like jar sealing. Jar sealing says, if you load a class from this package from this jar, you must always load all other classes in that package from that jar. So you're forced, you're having some control over what gets loaded, right? So that's worth looking into, right? If you still want to use serialization, if you're still desperate, then the other thing that we have for you is records, because records are just places. It's just got slots to hold data. Now, it doesn't stop all the attacks, but it does stop if your record class has no code to execute, then you've removed one possible attack vector, and it's a lot easier to deal with, to see. So you can use records, which is like another defense, which sort of was part of the reason for doing it. Right, what else have I got to tell you? Compile to native is a good way of doing it, because obviously you're not in the Java world anymore. There are some good pros and cons for it. Some people think it gets rid of all reflection problems like serialization, and some of that disappears, some of it can stay. But you give up a bunch of defenses. Like you gain fixed memory layouts. Your password is always going to be in the same place when it's instantiated, because you have repeatability, right? There are bits and pieces that I'd say from a security point of view are pros, but there are lots of cons. And especially if you set up to say, if you can have a fallback JDK, well, in which case, there's no real safety there at all. Right, and the bad guys can still get into build systems, so it's not it's a problem for everybody. But you can't assume that this is a panacea. It's got some benefits, but it has some negatives. Right, and finally, some secret weapons. So for some reason, this has turned up, and I don't know how it got into my deck. So I'll let you do this.
Okay, yes. So this is my slide again. Yeah. So. Like I said, we do JVMs and we do Java runtimes. And one of the things we thought about was, well, how can we take that ability to deal with the Java runtime and make it more secure? And we thought, well, the obvious way to do that is to say, well, we can identify exactly which Java runtime you're using, and we can make that available externally. So we started with the idea of, okay, it's the JDK, you're running JDK 8, let's say update 252. Now from that, we can then look at all the CVEs that have been reported against all the updates since then, and we could provide you with a list of the CVEs you're exposed to because you haven't updated your JDK recently. But then we thought, okay, let's take it one step further than that. And as Steve's quite rightly pointed out, the JDK and the JVM has a lot of this information internally that we can take advantage of. And if we look at Log4Shell, Log4j, one of the big problems that people had when that exploit came about was they suddenly said, oh, where are we using Log4j? And it might be that, they knew that they had written an application which had Log4j in it, so they could go, yeah, that's fine, and you can get a software bill of materials and you can do static analysis of your code. But when you run your application, do you know whether Log4j is actually being used? Yeah, sure. Log4j, probably the chances are if you've got it in there, you're doing some logging. But if it was a different library, maybe you've actually compiled that into your code, but do you know if the classes from that library are actually being used at any given time? So what we did with Azure Vulnerability Detection, we said, let's take all the information that's already in the JDK. So we're not imposing any additional load in terms of performance. There's no agent involved. And let's expose that information by, if you need to, forwarding it to a collector. And that way, when Log4j happens, or Log4Shell happens, next time, you can simply go, right, tell me all the machines I've got running right now, which are running Java, which have the particular library that is important loaded, and maybe even down to the class level where you need to know about a particular class that's being used in that application. So you can then get a report from that and say, right, these are the machines I've got to run around to very quickly and update these with the latest patch for that particular library. So that's what we've been doing with our Azure Vulnerability Detection.
Cool. And I'm allowing that in this deck because though it's a commercial pitch, the thing is, A, you should know about it, but B, other people could do this. It's the idea of adding more value to the system. So the other one, secret weapon, is Maven Central, right? Which is is that a commercial pitch? I'm not sure.
Might find that is actually a commercial pitch. Yes.
Oh, well, I don't know.
Who runs Maven Central?
Oh, Sonatype. Thank you. Right. So, and I mean, joking aside, Maven Central is one of the big, strong defenses because you have this stuff called malware, right? And this is real ones that get into repos. And there's a whole bunch of ways they do that, right? There's all different types, which I won't go over for now for time, but there's different ways of getting things into repos. And the thing is, if you go to Maven Central benefits because of all the stuff that Sonatype does commercially in terms of scanning for vulnerabilities, research for vulnerabilities. All that stuff is applied. So every time somebody uploads something to Maven Central, it goes through all our scanning systems. So currently you can't get better scanning and security from that point of view. And also because unlike most repos, to publish something into Maven Central, you have to own the domain and prove you own the domain. So therefore, it's very hard to fake things. It's not impossible, because there are things like typo squatting where you make a mistake. You spell it wrong. You switch 2 characters over in your POM. Well, if somebody's managed to register a domain that matches, then you're at risk. But generally, you have significant benefit just by writing code in Java and using dependencies because of the way that Maven Central works. Which I think, yeah, I've done okay. And there's one very, very last secret weapon, and that's you, right? And this is the takeaway. Right? We keep talking about Log4Shell because it's a great example. Currently, in fact, this number is slightly bigger. Currently, 31% of downloads of Log4j, 31% are for bad versions, old versions, vulnerable versions. So the secret weapon I want to leave you with is that you guys need to pay more attention to this problem, because you may think that things are safe, but it demonstrates that people in your organization, 33% of organizations in this room think they're safe or don't care and are downloading vulnerable versions of Java. So yes, you have a great JVM that's got lots of defenses, but it's still vulnerable if you don't keep on top of all the things that are coming down. All the patches are out there, and currently this is an example of we're not doing that good. So there we go. I think we're out of time. I had was there anything else to say? There are other things we could talk about, but I think that's probably the gist of it. Yeah, let's go to that one. Okay. Thank you. Any questions? I was going, no, it's the last day and I'm tired.
Oh,
yeah.
Got a question down the front.
Yeah.
Yep. No, you at the front. Yeah.
What?
Yeah, I thought I was waiting
Oh.
for the microphone.
Yeah, he's
Don't
not here.
think we've got one.
It's gone.
Yeah.
So shout.
You talked about keeping the vulnerabilities secret.
Yeah.
So, but obviously they do get publicised. What's the time period? When?
Oh, no. So what that means is that the actual details of the vulnerability, what the code vulnerability is not published. Well, eventually it's published, but we try and prevent you seeing it. So you see updates, and somewhere there'll be a list of 10 fixes, and one of them might be a fix to a vulnerability, but nobody will tell you over which one it is, because we're trying not to give the code away to the bad guys. And I think that's a laudable thing. We keep doing that. It's probably becoming less and less useful because of the exploit version.
Yeah, I mean, it's a little bit different with the OpenJDK itself, because we do publish the CVEs that are addressed in each
Oh
of
yes,
the,
but the secretness
is before the update is
it's
released.
about the detail,
Yeah.
not showing the detail until there's a fix.
Yeah,
Oh, wait, so when does it fix?
Yeah.
When you publish the details?
Yeah,
yes.
yeah. And I think you'll find that in all of these environments. Pretty much every time there's a vulnerability announced, there is a fix.
Yeah, unless you're a 0-day vulnerability.
Yeah, yeah. But
Which Log4j was,
yeah,
or Log4Shell.
yeah. But there was a fix day after. Yeah. Okay. Okay. Sorry. If you have any more questions, then we have booths.
We do.
Booth I?
Yes, we have booths downstairs.
Yes.
Come and talk
Please
to
come
us.
and talk to us. Otherwise, we'll get out of the way for
The next.
the next speakers who are here patiently waiting for us to do so. Thank you. Thank you very much.
Great. Thank you.